Now today what we will be doing is we'll be continuing optics, right? So we'll look at refraction through spherical surfaces such as a thin lens, right? So what is a converging lens and what is a diverging lens?
A conversion lens is a lens that is thicker at the center than at the edges, and it brings together rays of light. And the divergent lens is thicker at the edges than it's thinner at the center than the edges, and it separates or scatters rays of light.
Right. And we also have two other terms we could describe these lenses with. Yeah, we can say it is convex lens or concave lens. So which one is convex and which one is concave?
Convergent is the convex lens and divergent is the concave lens.
Right, so the converging lenses are convex because they are thicker at the center, and diverging lenses are thinner. Concave lenses are diverging lenses because they are thinner at the center. Now, there were some terms that we need to know for calculations of distances in using the lens equation, and also when we're drawing ray diagrams there are some terms that we need to know, right? So what is the optical center of the lens?
The point at which always pass through to deviation.
Right, so at different points in the lens, because of refraction, the light deviates, but when the light passes through the optical center, there is no deviation. What is the principal axis of a lens?
An imaginary line that's perpendicular to the lens and passes through the center.
Right, so yes, imaginary line perpendicular to the lens which passes through the optical center. What is the focal point of a lens?
So I said the focal length or the focal point?
Focal point.
The focal point is the point on the principal axis where the rays of parallel light converge or appears to diverge from after reflection or refraction.
Right, so basically if parallel light rays are incident onto a lens, they converge at the focal point. So that would be for a concave lens. For a diverging lens, there is no actual point at which they converge because by the nature of that diverging lens, they diverge. So in a diverging lens, the focal point is the point at which the light would have appeared to come from if the lens was not there. So the focal length of a lens is basically just the distance between the optical center and the focal point, right? And magnification, we know, is the ratio of the image height to the object height, and the radius of curvature is if we imagine the lens to extend and make a full circle, the radius of that circle is the radius of curvature. Right. So there is this sign convention that we saw when we were doing our equation, right? The lens equation. So what is the how can we calculate the focal length of a lens knowing the object distance and the image distance? What formula do we use?
So you'll use 1 on F is equal to 1 on U plus 1 on V.
Now, in this equation here, for this course, we have some conventions with the sign. So just like, well, for those of you who were in doing the second semester course, for thermodynamics, I strongly recommend you all stick to the convention we use in this course, because like ChatGPT or other textbooks, for example, they might have different conventions for what is positive and what is negative, right? So I want you all to stick to the conventions that I am using now for what a positive value means and what a negative value means. So images that are on the same side of the object are virtual images, right? And for virtual images, we have a negative sign for V, right? This is for images that are on the same side as the object. Right. Now, images that are on the opposite side of the object are we use that as positive, right? So right. Now, the object distance, we always take that to be positive, right? In the focal length, we take that to be positive for converging lenses, right? And we take the focal length to be negative for diverging lenses. Right? So when we are using this equation, this is the convention that we use, right? So we need to, well, I strongly recommend you all use these conventions. It could work with other conventions, but I strongly recommend using this, right? So while we have this equation up, let's say we have a light source, not a light source, we have an object.
So I have a question.
Yeah.
As it relates to images on the opposite side of the object, they are virtual as well or real?
Those are real images.
Okay.
Well, that would be for our simple cases, right? In when we're doing multi-lens systems, you could have virtual images on the opposite side of the object, but in our case, for these simple systems, the the image on the opposite side of the object are real. So that's why I didn't really mention it previously, because it is possible to not be real. Right, so let's say we had an object placed 15 centimeters away, 15 centimeters away from a lens. That has a focal length of 50 centimeters. Right? And we have to calculate the object distance, right? Sorry, the image distance. We have to use this formula above, right? So we need to substitute our values. Now, if the focal length and the object distance are in the same units, we can keep those units, right? So both of them in this case are in centimeters, so we can keep them in centimeters. So we would have 1 over v is equal to 1 over f minus 1 over u. This is 1 over 50 minus 1 over 15. As a fraction, this would be how much? This is negative 7 over 150, right? So V would be equal to negative 150 over 7 which would be equal to negative 22 and 4 over 7, right? That would be how much? 22 point how much?
So I have minus 21.4, not 22.
21.4. All right, yes. And the unit is centimeters, right? Because the focal length and the object distance were in centimeters. So now here we have a negative value for the object distance, right? Sorry, for the image distance. So what does this mean?
The image is virtual and upright and on the same side as the object.
Right, so if we had to draw this image now, this image would be on the same side as the object but a little further away, right? And it is upright as you mentioned, so it might be over here where this would be 6.4 centimeters in addition to the 15 centimeters, right? So this is our virtual image, and the reason, just by looking at the diagram, we can know that this would be a virtual image because the position of the object relative to the lens is less than the focal length. So the focal length can only converge light that is further, light can only converge at the focal point if the object is further away than the focal length. But in this case, the object is closer to the lens than the focal point. So light from the object cannot converge to form a real image. So we have a virtual image in this case. Right. Now what if we have to calculate the power of this lens? How do we calculate the power?
One on the focal length.
Right, so the power is 1 over f, which should be equal to 1 over how much?
1 over 50.
So remember, for calculations with power, we need to make sure that the length is in meters, right? When we have to calculate power. So we'll convert 50 to meters. So that would be 0.5. Therefore, this would be 2, and the unit would be
Diopters.
diopters, right? So 2 diopters would be power. So we can only get power in diopters when the focal length is in meters. If we had to calculate the magnification, how do you calculate magnification?
This is minus V over U, sir.
Right. M is equal to minus V over U. So this would be negative 5. So we had V to be a negative number. So it would be negative times a negative number over U, which was 15. So this would be how much?
One 1.43.
1.43. And what's the unit for magnification?
It doesn't have any units.
Right, no units, because it's a ratio of distances. So this is a positive magnification we have. What does a positive magnification mean?
It's upright
Right.
and visual.
Yeah. So positive magnification means it's an upright image, and a negative magnification means it's an inverted image. Right. And well, we weren't given the height of the object, but if we had to calculate the height of the object, what formula do we use?
Minus V on U is equal to HI on HO.
Right. So we could use that formula to and substitute either HI or HO depending on what we were given to find the other one. Right, and in this sign convention here, H is positive if the object or the image is above the principal axis. If the object or image is below the principal axis, H would be negative.
So you can repeat that one more time, please.
If the object or the image is above the principal axis, then H would be positive, either HI or H0. If the object or the image is below the principal axis, then HI and H0 would be negative. So, like, let me draw it, right? So this, let me say this is the image, so this will be positive HI. If this is the image, this will be negative HI. So that's the image, right? For the object, this is positive H0, this is negative H0. If this is our lens in the middle, you could see. Right, and that is the principal axis. Okay, so now we could move on to the human eye. So we know the function of the human eye, how it works, right? So first, the light is incident onto the cornea, and most of the refraction is done by the cornea. Because there's a large difference in the refractive index of the cornea compared to air, right? So the cornea does most of the focusing of the light entering the eye. After entering the cornea, it travels through the aqueous humor and then through the pupil towards the eye. Now the pupil, the size of the pupil is adjusted to allow more or less light to come into the eye. Now the lens itself of the eye, it fine-tunes that focusing of the light so that the image is focused on the retina, right? So ciliary muscles adjust the size of the lens so it can make the lens long and thin, or it can make it short and curved. So when the lens is long and thin, there's less refraction being done by the lens. So when the lens is long and thin, that allows us to see far. when the lens is short and curved, more refraction is done by the lens. So we are able to see close objects, right? Now, as we age, our ciliary muscles get weaker. So we are not able to make our lens curve as much as when we are younger. So as we age, we are not able to focus clearly on objects that are very close to us. And then, so this image is formed at the back of the eye, right? This is formed on the retina. The retina has it has something called rods and cones, which detect the intensity of light as well as color of light. And these are converted into electrical signals, which is sent through the optic nerve to the brain. Right? And there's a point at the center of the retina where the cones are packed closely together, and at that point there's the greatest amount of sharpness. Right? So I think yesterday someone asked a question about the human eye, how much detail you need to know. So you need to know just basically what I said, but focusing more on the refraction part, right? So accommodation, right? So I'll say it back again, right? Accommodation, we know, is the ability of the lens to change the focal length. So we could view an image on that, we can view an image of objects that are either near or far away, right? So both of these, light from both of these images can be focused on the retina due to accommodation, right? If our lens could not change focal length by being adjusted in size and shape because of the ciliary muscles, we would not be able to focus on both near objects and far objects, right?
Sir,
Yeah.
I have a question. Out of curiosity, like if you purposefully try to like differentiate your accommodation, like you put something close to your eyes, like really close, and try to read it, and then you put that same thing far out, like would that cause any damage? Well, not damage, but like would that hurt? As in, like, you're continuously doing it on purpose.
If you keep trying to focus on things close, like very close to you, after a while your ciliary muscles will get tired. I wouldn't really say damage, because that some people actually do eye exercises to prevent this the ciliary muscles getting weaker with age. So if you do it in a controlled way, it could actually be beneficial. But if you do it too much, like try to focus on an object close to your eyes for too long, then it could cause your ciliary muscles to get tired. And if you do it repeatedly, it could possibly even cause your lens to be more curved, to retain a more curved form, so it would not be able to flatten out well to look at distant objects. But that would be, you'd have to do that continually over a long period of time. So, but like for example, if you are looking at close objects in a room all of the time, if you're not going outside or looking at anything distant even in the room for a long time, it is possible that your lens retains a curved shape and you will be basically short-sighted. But yeah,
Thanks.
no problem. So, right. So you need to know accommodation. No accommodation in detail, right? So how the lens, well, you need to know that the cornea does most of the refraction because it has the highest refractive index, and that the lens changes shape due to the ciliary muscles, and that allows us to focus light from distant objects and near objects on the retina, right? And the retina turns it into an electrical signal that goes to the brain. And basically the lens would be more curved to focus on near objects, and it would be more relaxed to focus on far objects, and the ciliary muscles is what changes the shape. Right, now also in accommodation there is a limit to how close that we can view images, right? So when you are very young and your ciliary muscles are very strong, you can view objects very, very close to the eye, maybe less than 5 centimeters to your eye, right? Now, as I mentioned, as you age, that distance gets further and further because of because of age, and the ciliary muscles are weaker. So in general, we use a near point of 25 centimeters. Now, as being our age, we are able to view closer than 25 centimeters, but just in general, the near point is 25 centimeters. Now, I don't expect you to know the near point as 25 centimeters. I'm just stating it. And the far point, so we should be able to view things that are far, and that should not change with age, because for objects that are very far, our ciliary muscles have to be relaxed. And so even if the ciliary muscles get weaker, it doesn't take effort to relax. So even with age, we are still able to view distant objects, right? So now we have we went through some defects in vision, right? So if someone can only focus on close objects, what defect do they have in their vision? Myopia, right? Also known as short-sightedness. Now, how can we correct this short-sightedness or myopia?
A concave / divergent lens is put in front of the eye.
Right. So in myopia, this could the person can only focus on close objects, because possibly of two reasons: that the eyeball is too long so that the image falls in front of the retina, or it could be that the power of the lens is too strong, right? And the lens is not able to relax. The ciliary muscles are not able to relax to lengthen the lens, to flatten the lens. So to correct short-sightedness, we need a diverging lens that is able to help. So in the short-sighted eye, because the image falls in front of the retina, we need something to make the light diverge. So therefore we have to put a concave lens in front of the eye so that the light would now be focused further away, which would be on the retina. Now, if someone can only focus on distant objects, so basically, as I was saying, with age, this happens, right? What is the term we use to describe this being able to only focus on distant objects?
Long-sighted.
Right, long-sightedness. And how do we correct this?
Using a convex or converging lens.
Right, a converging lens. And this is because long-sightedness could happen if the eyeball is too short or the refractive power of the eyeball is too weak. Of the lens is too weak. So if the so basically the lens cannot be curved enough to cause the light to be focused on the retina. So we help the lens to be curved in a way by putting a converging lens in front of our eyes. So this would allow the image to be formed on the retina. Right. Now there's a term for this lack of accommodation when your age increases, right? So this is called presbyopia, right? Not sure of the pronunciation, but presbyopia. Right, this is basically what I was mentioning before. Then we saw there is astigmatism, where a person has difficulty in focusing light rays in different planes at the same time because of the uneven surface of the cornea, right? And that is corrected through a cylindrical lens. We looked at some equipment used for the eye. We looked at contact lenses, which basically are lenses that have no distance between them and the eye. They are put directly onto the eye. And we looked at LASIK, right? So what is LASIK surgery, and how is it used to correct eye defects?
So LASIK surgery is laser assisted in situ keratomelysis, and it's used to change the shape of the cornea. Like for myopia, it flattens the cornea, and for hyperopia, it steepens it.
Right, yes, so that is correct. So the a laser is basically used to flatten the cornea to correct myopia, and the laser could also be used to steepen the cornea, so basically make it more curved for hypermetropia, right? If the person has that. Yeah.
As it relates to the examination equipment, right? Do we have to learn every single one, and would you specify like how you just specified LASIK eye treatment, or is it that we may have to learn one exam and we just have to explain that?
You don't really need to go into much detail in these examination equipment. So because this isn't really something too testable in the exam. You just basically know what it is. So, but the detail into it, you don't really know. Like how in the notes there's a whole paragraph about it. You don't really need to know the full paragraph about it.
Okay.
So,
But like
to add
LASIK, you
to
should,
that,
yeah.
to add to that, is it like generally, like for example, the fracture or the refractor or LASIK, like should we have to pay one or you're specifying LASIK? Like just know the basics about it.
For all of these, you should just know the basic. But for LASIK, you should know the detail about LASIK. But for the examination equipment, you just know the basics about it.
Okay.
Right, so someone, let's take a question. Someone looking at an object, the power of someone's eye looking at an object is 50 diopters. Right, so they are looking at an object. Let's say, I don't need to draw this, right? They're looking at an object and it is the power of the person's eyes is 50 diopters. The lens to retina distance is 2 centimeters, right? So how far is this object from the person's eyes? How do we calculate this?
By using P equals 1 over U plus 1 over V.
Right. And what do we use as the image distance?
Zero 0.02 meters.
Right. So 1 over 0.02 is how much? Sorry?
50.
Oh, 5. Okay, let me change this question because otherwise it wouldn't really make sense. So it would be 52 diopters, right? So this will be equal to 2. Therefore, U is equal to 1 over 2 meters is equal to 50 centimeters. Right? Okay, so let us take a break and we will start with electricity. So we can start back at 10 past 9. So let me just write it back. So the equation is P is equal to 1 over U plus 1 over V. Right? Now, the value of P we got was 52. Right? Then U is 1 over U. We have to find this. And then we add 1 over. Now the value of V itself is 0.02. Right? But V is in the denominator of the fraction. So we write 0.02 on the bottom of the fraction. Now we saw that 1 over 0.02 is equal to 50. Right. So now we can rearrange this equation. 52 minus 50 is equal to 1 over U. Right. So 1 over U is equal to 2. Right? So it's actually 1 over U is equal to 2, not U itself. So to find U, then we have to take 1 over 2. So 1 over U is equal to, U would be equal to 1 over 2. We take the inverse of both sides. Now this would be in meters, so this is 0.5 meters. So this would be 50 centimeters.
Okay, sir.
Okay, so let's continue with electricity.
Excuse sir.
Yeah.
I have a question, right? So for the lens question, right? How last year for the exam you had bring the diagram first to draw? Is there any diagram first to draw at this exam?
No, you wouldn't need to draw the diagram in this one. For the lens
Okay,
question
done.
at least. Right. So we saw there that this semester we saw there are point charges, for example, electrons and protons. These have a quantized charge, right? So the electron has a fixed charge of 1.6 by 10 to the negative 19 coulombs negative, but the proton has the same charge except that it is positive, right? So we saw that we can write charges in the form of a multiple of this magnitude, right? We saw that basically charge is quantized. And well, in the the second semester, we saw that there is a law of conservation of charge, right? So that is the total charge in an isolated system is always conserved. We also saw this semester and last semester that these electric charges are described as point charges, like for example electrons and protons, because their size is very small compared to the distance between them. So we can consider them as point charges. And we saw that electricity results from either imbalance of the amount of charges, so that would be like static electricity, where electrons move out from an object into another object, so one object becomes positively charged and another becomes negatively charged. And there is dynamic electricity, which occurs due to the flow of electrons. We also saw a law which is called Coulomb's law, right? So what is Coulomb's law?
Force of attraction between two charged particles placed at a distance, directly proportional to the product of charges.
Right, is directly the force of attraction or repulsion between point charges is directly proportional to the magnitude of the charges, but you left out one other part of that definition, which is that it is also inversely proportional to the distance between, to the square of the distance between them. So we could write that as F is equal to a constant. Well, F is proportional to the magnitude of charge 1 multiplied by the magnitude of charge 2 over r squared. And we could write this as F is equal to a certain constant, which we have 1 over 4 pi epsilon naught by Q1 Q2 over R squared. Right.
So if you ask the state Coulombs, or we could just write this formula and define the variables, right?
Yeah, so you could do that because the worded definition is basically just explaining this equation. Right. So we saw Coulomb's law, and basically utilizing Coulomb's law is substitute values into here. So let's say, for example, we have a charge Q1 and Q2 are 0.2 Coulomb charge, and this one is both of them positive, a 0.3 Coulomb charge separated by 4 meters, right? And we have to find the force of attraction, the force of repulsion between them, because these are both positive charges. We can just substitute into this, right? So 1 over 4 pi epsilon naught multiplied by 0.2 times 0.3 over 4 squared, right? So you need to remember the square. So this would be what value?
What's the value for epsilon naught?
Oh, epsilon naught. So this is 8.85 by 10 to the negative 12. Now how much would that value be?
Four 4.16 by 10 to the minus 13. I'm working out the units.
1 point how much? 16 by 10 to the
4.16
4 point.
by 10 to the minus 13.
I think something. It shouldn't, remember this is epsilon naught is to the power of minus 12, right? And this is 1 divided by 4 pi epsilon naught. So when you're doing this, put this piece in brackets. 1 over that piece in brackets.
So for 1 over 4 pi epsilon naught, couldn't you not just use Coulomb's constant of 8.9876 by 10 to the 9?
You could use that, yes, but you need to remember that because
You're not giving us that.
no, you're not really given that separately.
Okay.
Because that's just a mix of other known constants. It's not really like epsilon naught is used in many different things. This Coulomb's constant is only specifically for this equation. Right, it's 3.37 by 10 to the 7 Newton. Right. Now these are very big charges, right? 0.2 coulombs and 0.3 coulombs. If we look at the charge of our electron, it's by 10 to the minus 19, right? So just for simplicity, I use these charges for the practice question. So that is why we basically got a very large force like this, right? So we also saw different methods of charging, right? We saw triboelectric charging, charging by conduction, and charging by induction, right? So how would you briefly explain triboelectric charging?
Object A loses electrons and gives them to object B.
Right, yeah, so there's rubbing off each other and rubbing off two different objects, and one loses electrons and one gains electrons, right? So one becomes positively charged and one becomes negatively charged. Right. What about charging by induction? Right, so charging by induction, we have two neutral metal spheres that are in contact with each other, and then a charged object is brought close to these two spheres. Now because these spheres are metallic, electrons can flow in the spheres. So let's say, for example, it was a negatively charged object brought next to the spheres, it would cause the electrons to be repelled. So one sphere would become positive and one sphere would become negative. So then the objects can be removed and the spheres can be separated, and it's charged like that. We can also charge through induction with grounding, right? So we could, in this case, we just need to have one sphere and we bring the charged object next to it, and this causes an imbalance of the, not an imbalance, the electrons in the sphere redistribute. So if we bring a negatively charged object close to the sphere, the electrons move away from that object, and if we ground that object, some electrons would leave the sphere. So if we remove the grounding afterwards, the sphere would be positive. Right, so let's move on to electric fields. So we saw last semester and this semester that the electric force is equal to Q times E, right? We saw this both semesters. So we could also write, using this, we could write the electric field to be Q over 4 pi epsilon naught R squared, right? We could write the electric field to be in this form. Now, when we are drawing electric fields, we have a convention that the electric field lines, they start from a positive charge and they end on a negative charge, right? So if we have a positive charge, they go outwards from a positive charge. And if we have a negative charge, they go into the negative charge, right? What are some other properties of electric field lines?
They do not intersect.
Right, they do not intersect. And what else? When they are closer together, what does this mean?
Stronger electric field.
Right, so closer together means a stronger electric field, further apart means a weaker electric field. Right. So let me just go back to this question real quick, right? So in a question like this, you could get, instead of having it in coulombs, you might see microcoulombs or millicoulombs, for example, right? So remember, in this type of question, if you have microcoulombs or millicoulombs, for example, you need to convert it to coulombs to be able to put it in Coulomb's law, right? So for Coulomb's law, all of your units has to be in SI units. So you need to have the charges in coulombs and we need to have the distance in meters, right? So if the distance is given in centimeters or kilometers or anything like that, it must be converted to meters. And any other form of coulombs, so microcoulombs for example, needs to be converted to coulombs. Right. And as I mentioned in this question here, there are two positive charges, right? So because as we know, we saw this the last semester and this semester, positive charges repel, like charges repel and unlike charges attract. Right, so let us move on now to resistance. So what does the resistance of a conductor depend on? Before we go to that, what is the resistance of a conductor?
R equal V over R.
Sorry, can you
The
repeat?
voltage R is voltage over current, and then the ratio of voltage is the current going through it.
All right, so that is using Ohm's law to give right, that's
So
using
it's the resistance of a conductor is what opposes the current flowing through the circuit.
right. So the resistance of a conductor is what opposes current flowing through the circuit. So we could write out that we can quantify that resistance using Ohm's law, right? So in Ohm's law, we have V is equal to IR. So we could also define the resistance. We can quantify the resistance as the ratio of the voltage across the conductor to the current flowing through the conductor. Right? So this is what resistance is. Resistance is basically what opposes current flowing through the circuit, which is equal to the ratio of the voltage across the conductor to the current flowing through it. Now, what factors affect the resistance?
So temperature, the material the conductor is made of, and probably the size.
Right. So, well, we didn't do this direct formula, but I'll still write it. R is equal to rho L over A. Right? So in this formula, we have this value here, rho, is resistivity. So you don't need to know this formula, but I'll just explain it with this formula. Rho is resistivity. So resistivity depends on the material of the conductor. Right? So different types of material have different resistances. Then we have L divided by A. So L and A is the length and the surface, the cross-sectional area of the conductor. So basically, the resistance depends on the size of the conductor. A longer conductor would have a larger resistance. A conductor that has a bigger cross-sectional area, so basically it has a bigger diameter, thicker conductor would have a smaller resistance, right? Then we also saw in the first semester that resistance depends on temperature as well. So temperature is a thermometric property of some thermometers, right? Resistance is a thermometric property of some thermometers, right? So for example, the platinum resistance thermometer, when the temperature increases, the resistance decreases, right? But the resistance changes with temperature. It depends on the material itself. So the resistance of a conductor depends on the type of material the conductor is made of. It depends on the temperature of the conductor, and it depends on the dimension of the conductor. So the length and the cross-sectional area of the conductor. So in a series circuit, if we have two resistors in series, and this is R1 resistance, R1 and R2, what is the equivalent resistance? How do you calculate that?
So isn't that just R1 plus R2?
Right, R1 plus R2. And if we have them parallel now, so let's say we have R3 and R4. What is the equivalent resistance in this case?
One over R3 and 1 over R4. Plus 1 over R4.
Right. So let's say we had a circuit like this. This is a 2 ohm resistor, this is a 3 ohm resistor, and this is a 4 ohm resistor. How do we determine the equivalent resistance of this circuit?
You go do 1 over 3 plus 1 over 4, and whenever I get that, you just add it to 2.
Right, 1 over. Right, so I will write Req P for the parallel one is equal to 1 over 3 plus 1 over 4. So this is equal to 1 over 7 over 12, which is equal to 12 over 7. Spencer given trouble now. Right, 12 over 7 ohms. So then the total resistance, I just write in Req as T for total equivalent resistance, would just be 12 over 7 plus 2, which would be equal to 3 and 5 over 7 ohms, which is how much ohms as a decimal?
$3.714.
Right. So basically, for any question like this, you split it up into the either parallel or series, and then after you do the calculations, right? So in this case, we saw that we could calculate the equivalent in parallel first, and then after use this as a resistor with equivalent resistance 12 over 7 ohms, and then it would be in series with the 2 ohm resistor. There might be cases where we could do the series resistance first, and then after we would realize they are in parallel with another resistor, right? So like for example, if we had a resistance like this, in this case we would do the series resistance first. So we would calculate the equivalent resistance of these two resistors, and then after we would see it's in parallel with the third resistor, so we could calculate the equivalent resistance of the entire circuit. Now in this question here, the question with the numbers that I gave earlier, is the current flowing through the 2 ohm resistor and the 4 ohm resistor the same? Okay, let me actually do it for this. In this here, right? So let's say we have, this is 1 ohm, this is 2 ohms, and this is 4 ohms, right? Is the current flowing through the 4 ohm resistor and the 1 ohm resistor the same in this circuit?
Yeah.
So actually the current is not the same flowing through these two circuits, right? Because let's say the current is flowing in this direction. At this junction here, the current has to split between the top two resistors and the bottom resistor. If the equivalent resistance of the 2 top resistors was the same as that of the bottom resistor, then the current would be the same, right? But now the equivalent resistance of these top 2 resistors is 3 ohms, right? Because they are in series, so 1 plus 2 is 3. So there is because these are in parallel, there is the same potential difference across both of them. So V is the same in the 3 ohm resistor and in the 2 ohm resistor. But because R is different, there would be a different amount of current flowing in the top as the bottom, because we know I is equal to V divided by R. So although V is the same, R is different, therefore there would be a different amount of current flowing through the top resistor and the bottom resistor. Now if the bottom resistor was, instead of 4 ohms, if the bottom resistor was 3 ohms, now the equivalent resistance of the top and the bottom resistor, the top 2 resistors and the bottom resistor, is now the same. So now the current coming at this junction here, it splits equally to the top and the bottom, because R is the same and V is the same across both the top and the bottom of the circuit. Therefore, in this case, the current will be the same through both resistors. Right, so let us move on now to Kirchhoff laws. So we saw there are 2 laws, 2 of Kirchhoff's laws. There's Kirchhoff's current law and Kirchhoff's voltage law. So what is Kirchhoff's current law?
So the total current leaving a circuit is equal to the total current. The total current entering a circuit is equal to the total current leaving the circuit.
Okay, so not a circuit, but it would be the circuit's junction, right? A junction in the circuit. So the total current entering a junction in a circuit is equal to the total current leaving that same junction in the circuit, right? So we could draw that. Well, actually, we don't need to draw it. We see in it here. In the same diagram, with the same explanation as I was given before, right? The amount of current I that is going into this junction here in this circuit is equal to, let's say, I1 goes upwards and I2 goes downwards, right? So then Kirchhoff law states that I is equal to I1 plus I2. Right, that's what Kirchhoff's law says. So the total current going into the circuit, which is I, is equal to the current the total current going into that junction of the circuit, which is I, is equal to the total current leaving that junction, which in this case is I1 plus I2. Right, so another way of stating it, in a parallel path, the total current entering the circuit's junction is exactly equal to the total current leaving that same junction. Right. So what about Kirchhoff's voltage law?
In a closed loop series, the total voltage equals 0.
Right. So the sum of all the voltages around a closed loop in a circuit is equal to 0. Right. So let's take a small example of that, right? So we have a 6 volt power source here, and we have a .3 volt. We are told we measure the potential difference across. We measure the potential difference across this resistor. So we have V here, and we see that here this potential difference is equal to 3 volts, and we want to find the potential difference across this one, right? So let's label this V1. We want to find what is V2, the potential difference across that resistor. So we can take the loop to be in this direction, right? So now across this battery in this direction, we are going from low potential to high potential, right? We go from the smaller line to the bigger line. Therefore, we would have a negative voltage, right? When we go from low potential to high potential, we would have a negative voltage. So -6 plus the potential across R1, which is V1, which is 3 volts, plus the potential across R2, the potential difference across R2, which is equal to V2, is equal to 0. Right? So this is the sum of the voltages across this closed loop. So we have negative 3 plus V2 is equal to 0. So V2 is equal to 3 volts. Right, so this is just a simple application of Kirchhoff's voltage law. Right, so now let us move on to capacitance. So what is the definition of capacitance?
The ratio of magnitude of stored charge to potential difference.
Right, so we could write that out as capacitance is equal to the ratio of the magnitude of the stored charge to the potential difference. So C is equal to Q divided by V. And the unit of capacitance is what? The SI unit.
Farad.
Right, the farad. Now we also saw parallel plate capacitors, right? So in parallel plate capacitors, we basically have two conducting plates next to each other, and they are separated by some medium. That medium is called what? In a parallel plate capacitor, the medium that separates the plates is called
Is it the dielectric material?
Yes, so it's called a dielectric. Now, the capacitance of a parallel plate capacitor, how do we find the capacitance of a parallel plate capacitor in terms of the separation between the plates and the surface area of the plates?
C equals the EO area over D.
So epsilon naught A over D, right? Where epsilon naught is the same epsilon naught we saw earlier. A is the surface area of the plates and D is the separation of the plates. Right? Now, if there is a dielectric medium, then the capacitance, it changes by a factor called kappa, right? So it increases by that factor called kappa. So if we have a capacitor a 1 microfarad capacitor that has a surface area of 5 has a surface area of 5 millimeters squared, separated by a distance of actually right so if we want to determine so we have a capacitor that has a surface area of 5 millimeters squared. It is separated by a distance of 0.5 millimeters, and we apply a potential difference across it of 20 volts, and we want to determine the charge stored by this capacitor. So determine the charge stored in the capacitor. How do we do this? What's the first thing we need to find?
Is it C?
So we would need to first find the capacitance of this capacitor, right? So we substitute in this equation here. Now we assume if it was not given to us, we would assume the dielectric is A, so kappa would be 1. So you could write C is equal to 8.85 by 10 to the negative 12 times A, which is 5 millimeters squared. But we need to convert that to, sorry, the V is 0.5 millimeters, right? We need to convert millimeters squared into meters squared, right? So that is equal to 5 by 10 to the minus 3 squared divided by the distance, which is 0.5 by 10 to the minus 3. Right? So this actually cancels with this. So what we would get is 8.85 by 10 to the minus 14 coulombs. Right? And then now we use the formula Q is equal to C times V. So Q would be equal to 8.85 by 10 to the negative 14 times 20. So this would be 1.77 by 10 to the negative 12 coulomb. Sorry, the unit for capacitance is farads, right? Right. Now I didn't do any questions with Ohm's law, right? So let me just quickly do a Ohm's law question and we will move on. So if now the capacitor has a resistance of, actually not the, if we know a current of 0.5 amps flows through the capacitor, right? Let me put resistor. And with a potential difference of 20 volts. To calculate the resistance, we use Ohm's law, right? R is equal to V over I, which in this case would be equal to 20 over 0.5, which would be equal to 40 ohms, right? So that is a simple question on Ohm's law. So let us move on now to capacitors in series and parallel. So if we have two capacitors in series, C1 and C2, what is the equivalent capacitance?
One over C1 plus 1 over C2.
Right. And if we have capacitors in parallel, C3 and C4, what is the equivalent capacitance?
C3 plus C4.
C3 plus C4, right? So we could see that it's basically the opposite of resistance, right? In series, for resistance, the equivalent resistance was the same formula as for the capacitance in parallel, and vice versa, right? So we did a question with resistance already. For capacitance, it's basically the same principle, except you're replacing the series formula with the parallel formula. So I wouldn't really go into another question on that. Right, so that is it for electricity. So we can take a 10-minute break now. We'll come back at 20 past 10 and we will do magnetism.
So, excuse?
Yeah. Yeah.
So, for these, for this, section we're doing here, right? By chance, we have to know, like, if it, you have to learn if it, like, the discharging and, charging for the exam.
For the exam, I wouldn't really cover that in the exam.
Okay, done.
Okay.
Excuse me, sir.
Yeah.
Could you check your private chat, please?
Okay.
Excuse sir.
Yeah.
Just to clarify, so far we don't need to know any diagrams. Well, the electric field, I know you do a diagram on your iPad. That's the only one we have to know so far, or?
Yeah. So like the diagrams with positive and negative charges next to each other,
Yeah.
like that you wouldn't really need to draw that. You'd have covered something similar for magnetism in the lab already. So wouldn't
Oh,
have that in the this exam.
okay. Thank you, sir.
Okay, no problem. So we know a magnetic field is a region around a magnet where magnetic force is experienced, right? Now we saw that magnetic fields vary from electric fields in one big way. So what is that one big way that magnetic fields vary from electric fields?
So what was the question?
In what way does magnetic fields vary from electric fields? If you're drawing, let's say you have to draw electric field lines versus magnetic field lines, what is the big way that they vary from each other?
Is it the lines go from north to south?
Right. So in magnetic fields, the lines always go from north to south. There's nothing like a magnetic monopole, like nothing like a north pole only or a south pole only. Whereas in electric fields, we can have a positive charge only or a negative charge only. There's not necessarily have to be a positive and a negative charge. But in magnetic fields, anytime there's a north pole, there will always be a south pole. Right? As we say, there's nothing like a magnetic monopole. So we also saw there are different types of magnetic materials, right? So what are the three types of magnetic materials? And give a brief description of them.
So paramagnetic materials are weakly magnetized in the same direction. Diamagnetic is weakly magnetized in the opposite direction, and ferromagnetic is strongly magnetized in the same direction.
Right. So ferromagnetic materials such as iron are strongly magnetized in the same direction as an external magnetic field. Paramagnetic materials are weakly magnetized in the same direction as the external magnetic field, and diamagnetic materials are weakly magnetized in the opposite direction to the external magnetic field, right? So you would need to make sure you mention to the external magnetic field when you are stating that, right? Now we also saw that the earth is made up of iron nickel alloys in the core, and it produces a magnetic field as well, right? And we also saw diagrams on how to draw magnetic field lines, right? So let us move on to magnetic flux. What is magnetic flux?
Magnetic flux is the strength of the magnetic field.
Right, so magnetic flux is basically a measure of the number of field lines passing through a certain area, right? Now, what is the formula for magnetic flux?
The angle equals BA cos angle.
Right. So phi is equal to BA cos theta, right? Where if we have a surface If we have the surface, let's say this is the surface here. I'm trying to draw a 3D diagram on a 2D. Right, so this surface has an area of A, a surface area of A. There is a normal to the surface, and the angle theta is the direction of the magnetic field passing through the surface towards the normal, right? So let's say the direction of the magnetic field was like this, then this is the angle theta here, right? So if the magnetic field is perpendicular to the surface, cos of theta would be equal to 1, and this formula would be phi is equal to B times A. Now let's say this surface was actually multiple loops of wire, right? So we had multiple loops of wire. Let's say there are n loops of wire. Then the magnetic flux would actually be n times B times A cos theta, right? The magnetic flux in that set of wire, because each turn of wire experiences the magnetic flux B times A times cos theta. So if there are n loops of wire, the total magnetic flux would be n times B times A times cos theta. So let's do a simple question on that. If, let's say for example, B is equal to 0.4 Tesla, theta is equal to 90 degrees, and the surface area is equal to 0.5 meters squared. Phi now would be equal, let's say the n is one loop, right, is equal to 0.4 times 0.5 times cos of 90. This would just be equal to 0.2. And what is the unit for magnetic flux?
WB.
Right, Webers, right, WB. Right, we also saw two laws. These laws are Faraday's law and Lenz's law. So what does Faraday's law state?
Change in magnetic flux induces EMF.
Right, so any change in this magnetic flux induces an electromotive force in a circuit, right? So the magnitude of that induced electromotive force is directly proportional to the rate of change of magnetic flux, right? So some ways we could change the magnetic flux is by changing the magnitude of the magnetic field, changing the area of the wire, or changing the angle between the magnetic field and the wire, right? So just by looking at this equation here, we could see that we could change B, we could change A, we could change N, and we could change the angle, right? We could also change, because Faraday's law says that it depends on the rate of change of magnetic flux, the magnitude of this EMF could also be changed, increased or decreased by changing the rate at which we change this magnetic flux. So if we increase the angle very quickly, we would have a larger EMF, for example, right? Now, that induced electromotive force in the wire, that also produces its own magnetic field, right? Because as we know, any motion of current, any motion of charge produces a magnetic field, and current is motion of electrons in a conductor, right? So that produces its own magnetic field. So then we come to Lenz's law. What does Lenz's law state?
The magnetic field opposes the magnetic flux.
Right, so that the magnetic field created by the induced EMF opposes the original magnetic flux, right? So if we have to write out these two equations, these two laws in one equation, how would we write this? Faraday's law and Lenz's law.
So the sign for EMF is like a easy
Right, epsilon
equals right minus N D the hook sign thingy over dt.
Right, so basically the electromotive force acts in the opposite direction, so we have the negative sign, is equal to N times the change in magnetic flux with respect to time. Right.
So where I have phi, there's a different symbol in the notes. I don't know the name of it though.
In the notes, let me see. Oh, the notes has this. Right, so you could write it as either one. It's just like as we know, when we write out the equation, we need to define the symbols, right? So when we write epsilon is the EMF, right? N is number of turns, T is time. So all we would do is just define this to be the magnetic flux, right? We could also write this to be the magnetic flux. So when we write the equation, we define what the symbol means, we can it would be okay. You could use either symbol basically. Right, so let's move on to the magnetic flux patterns. So as we know, in a current, as I mentioned just now, any motion of charge creates a magnetic field. So therefore, current flowing in a wire would also create a magnetic field. Now, how do we determine the direction of the magnetic field of the current in the wire due to the current in the wire?
The right hand.
Right, the right hand rule. So we do like if we're gripping something in our hands, so the direction our thumb points, which is upward, would be the direction of the current, and the direction which our fingers curl, that would be the direction of the magnetic field, right? So we call that the right hand thumb rule or right hand grip rule. Now, so if we have a current flowing this way, according to the right hand rule, will the magnetic field be clockwise or anti-clockwise around this current carrying wire? Actually,
Is it anti-clockwise?
yes, so it would be going anti-clockwise around, right? So like this. Right? So we know that there are symbols we use to have current flowing into the page or out of the page, right? So what is the symbol for current going into the page or the magnetic field going into the page?
An
X.
X.
An X, right? And the symbol for it coming out would be the dot, right? So if we have to draw the magnetic field around a current carrying wire that carries current into the page, would that be clockwise or anti-clockwise?
Clockwise.
Right, so it would be clockwise, right? Now, if we have another wire also carrying current into the page, so if we bring another wire with the same direction of current, the magnetic field would now be drawn like this, right? So this someone had asked a question before about diagrams. So the diagrams for the electric field I mentioned, they would not have been coming, right? But you should know for the exam, you should know how to draw the magnetic field around current carrying wires. You should know how to draw the magnetic field around one current carrying wire. You should be able to draw it for two wires carrying current in the same direction, and you should also be able to draw it for the two wires carrying current in opposite directions, right? So in this case here, we have two wires carrying current in the same direction. So you all should be able to do this, right?
Yes, repeat that if you don't mind.
You would need to know how to draw the magnetic field around one current carrying wire, also around two wires carrying current in the same direction, and also around two wires carrying current in opposite directions.
Okay, thank you, sir.
Okay, no problem. So in this case, we have like currents, do they attract or do they repel each other? Current that is flowing in the same direction, would these wires attract or repel? like currents, do they attract or do they repel?
Repel.
So like currents, they actually attract, right? So when we draw any magnetic field lines, we have to draw them that the magnetic field lines actually come closer together. The magnetic field lines at the center kind of meet. Well, not exactly meet, but they are attracted to each other. So like this, you see at the center they are being pulled closer together, and then if we continue this magnetic field line, we would see now, if we draw a magnetic field line here, these magnetic field lines are now in the same direction, right? It's going clockwise about both of them. So these magnetic field lines, they actually join. So we could draw this magnetic field line like this. So they join together and it causes the force of attraction between both of them. Right? So these are like currents, they are attracted to each other. Now, unlike currents, we have to draw a diagram for these. So let's say this side is coming out of the paper and this side is into the paper. Now these magnetic field lines, they repel each other, right? So when we are drawing these, we draw the circles closer to the current carrying wire on the side of the current, the opposite current, and further apart away from the opposite current, right? So like this. Now you also need to make sure you include the directions of the magnetic field, right? So we see that these are unlike currents and they repel. Now we could also use the right hand grip rule to determine the direction that current flows in a solenoid. So if we have a solenoid and we place our fingers in the direction that current flows in the coils of the solenoid, our thumb points in the direction of the magnetic field that goes through the solenoid, right? So we could use that as well. So we have these as diagrams of the magnetic field lines flowing in the magnetic field lines around current carrying conductors. So how do we determine the magnitude of the current? Sorry, how do we determine the magnitude of the magnetic field around these current carrying conductors? So let's take back one, right? So this current conductor that carries current into the sheet of the paper. What is the magnitude of the magnetic field at this point P, if this is at a distance r from the current? What is the formula for the magnetic field? B is equal to
Is it the UOI over pi r?
right. B is equal to mu naught I over 2 pi r, right? So if we had a current carrying, if the current in this wire is 0.5 amps and we want to find it and the distance r is equal to 0.2 meters, the magnetic field would be mu naught times I. So mu naught is the permeability of free space, which is 4 pi times 10 to the negative 7 times the current, which is 0.5, over 2 pi times the distance. So in this distance is 0.2 meters. So this would be equal to five by 10 to the negative 7, and the unit of the magnetic field is
T.
Tesla, right? T. So that is just a simple example of that. Now if we have a solenoid, right? A solenoid with 250 turns carries a current of 2 amps, right? What is the magnetic field um 0.5 centimeters away from the solenoid? Radially away from the solenoid. 0.5 meters, sorry. What formula do we need to use to calculate this magnetic field? Oh, this solenoid has 250 turns with a length of 5 centimeters. What formula do we use for this?
Is it B equals to UO NI over L?
B is equal to mu naught N I over L. Right? So we could substitute 4 pi by 10 to the negative 7 multiplied by 250 multiplied by 2, and what are we dividing by?
meters.
Right, 0.5 meters. Right, so this would be equal to 4 pi by 10 to the minus 4 Tesla. Right, so right, that was an example of the magnetic flux, magnetic field around the solenoid. So we know an electromagnet can be made by winding a solenoid and turning on the current. We would produce a magnetic field, and turning off the current, the magnetic field would be turned off. Right? Now in an electromagnet, we have something called a soft iron core, a soft ferromagnetic core. Right? Now we use the soft ferromagnetic core because it is, as we saw earlier, ferromagnets are strongly magnetized in the same direction as an external magnetic field. So when these ferromagnets are placed in the core of the solenoid, the magnetic field due to the solenoid magnetizes that ferromagnet, and the ferromagnet now becomes magnetized in the same direction very strongly as that magnetic field in the solenoid. So it increases the magnetic field strength of the solenoid. Soft means that it is easy to magnetize, right? And it's also easy to be demagnetized. Whereas hard means it is not easy to be magnetized or demagnetized. So with a soft iron core, when the electromagnet is turned on, this ferromagnet, it can be magnetized very quickly. So the electromagnet gains its full strength very quickly, and it can also be demagnetized very quickly. So the electromagnet, it loses, it turns off very quickly, right? So that's why we use a soft ferromagnetic core. Right? Now the strength of the electromagnet, it depends on the number of turns of the solenoid, as we can see from this equation here. So as n increases, the strength of the electromagnet increases. It also depends on the current in the solenoid, right? So as we increase I in this equation, the strength of the magnetic field also increases. Right, so let us move on now to magnetic force. So we know that any motion of charge produces a magnetic field. So a current carrying conductor or motion of any charged particle in a magnetic field, they would produce their own magnetic field. So that would interact with the external magnetic field and there will be a magnetic force, right? So any current carrying wire in an external magnetic field or any charged particle moving in an external magnetic field experiences a force, right? And that force is termed the magnetic force, right? So what is the formula? Actually, before we go into the formula, so that force is maximum when the direction of the motion of the charged particle or the direction of the current is perpendicular to the external magnetic field, right? So, and the force is zero when the current is parallel to the external magnetic field, right? And we could see that because if the external magnetic field is into the plane of the paper, and this is the current carrying wire that is perpendicular to the external magnetic field, the magnetic field produced by the wire is now in the same plane as the external magnetic field. So there will be the strongest interaction. But say now the current carrying wire is placed like this and the external magnetic field is now upwards. The magnetic field produced by the wire is perpendicular to that external magnetic field. So there will be no interaction in this case. So we can use a rule to determine the direction of the magnetic force, right? We can use a rule with our hands to determine the direction of the magnetic force. So what rule is that?
Fleming's left-hand rule.
Fleming's left-hand rule, right? So in Fleming's left-hand rule, what does the thumb represent?
Direction of force.
Right, the direction of the force. The index finger represents what?
Direction of field.
Direction of magnetic field, and the middle finger represents
Direction of
the direction of the current, right? Which is the direction of motion of positive charge, right? Because for current we use it as conventional current. So for a current carrying conductor that carries current of magnitude I and it has a length L, what is the magnetic force of that experienced by that conductor in a magnetic field?
So repeat that.
So what is the formula for the magnetic force experienced by a conductor, a current carrying conductor in a magnetic field?
F is equal to BIL sine theta.
Right, F is equal to BIL sine theta. Right. So, okay, and now if it is a charged particle moving in a magnetic field, actually before we move on to the charged particle, so looking at this, the magnetic force depends on the magnitude of the magnetic field. It depends on the amount of current flowing in the conductor, so B and I. It depends on the length of the conductor, and it depends on the angle of the conductor to the magnetic field, right? So what is the magnetic force experienced by a charged particle moving in the magnetic field?
F equals to BQV sin up.
Right, F is equal to BQV sine theta. Now, so in this case, what does the magnitude of the magnetic force depend on? What factors does it depend on?
It depends on current, length, and angle.
No, for the charged particle moving in magnetic field, what does the magnetic force depend on?
The angle.
Angle is one thing, yes. What else does it depend on?
The speed of the particle.
Right, the speed of the particle. What else?
The charge.
The magnitude of the charge, yes. And one more thing.
Magnetic flux density.
Right, the strength of the magnetic field. Right. So we did questions like this this semester, but we'll do back another question with this, so we can just do some practice questions with this. So say we have a current carrying conductor carrying 2 amps in a magnetic field perpendicular to a magnetic field of strength 0.5 Tesla, and the length of this current carrying conductor is 3 meters, right? And we need to find the magnetic force on this current carrying conductor. We can substitute, right? F is equal to B, so that would be 0.5 times the current, which is 2, times the length, which is 3 meters. Now the current carrying wire is perpendicular to the magnetic field, so theta in this case would be 90 degrees, right? So now we would have this would be just equal to 6 newtons. Now let's say we had a charged particle, an electron moving in a magnetic field it has a velocity of 1.2 by 10 to the 7 meters per second, right? This is an electron with charge 1.6 by 10 to the negative 19 coulombs. Right, it moves in the same magnetic field of 0.5 Tesla. What direction would this electron curve in?
Up.
No, so it would not be up. We have to use Fleming's left hand rule, right? So what direction would we point our middle finger?
To the right.
No, so for current, for the direction of the current, we have it as this, we have to use conventional current, right? And conventional current moves in the same direction as positively charged particles. So, but the electron we know is a negatively charged particle, right? So if the electron is moving to the right, the conventional current is moving towards the left. So in this case, we need to point our middle finger towards the left. Now, the magnetic field is pointing in what direction?
Into the screen.
Into the screen, right? So we have our middle finger pointing towards the left, our index finger pointing towards the screen. So our thumb would be pointing downwards, right? Because this is Fleming's left hand rule. So the charged particle in this case would start moving downwards and move in a circle in this direction, right?
So we have to know to draw these in the exam as well, right?
Right. Yeah, you should be able to know to draw this. So you should know to draw this for both semester 2 and the semester 3 exam, right? Because this was covered in both semesters. We did this at the start of semester 3 as well. Right. So the magnetic force experienced by this particle would be what? F is equal to, what values do I need to put in?
The strength, the charge and speed.
Right, so the magnitude of the field is what? 0.5. The speed, the charge is 1.6 by 10 to the negative 19, and the speed is 1.2 by 10 to the 7. Now, this is moving perpendicular to the magnetic field, so sine 90 would just be 1, right? And this is equal to what?
(9.6 by 10 negative 50).
And the unit is
And
newtons, right? So always make sure to write the units as well. Now let's say the electron, or let's say now we have a proton, right? Moves at an angle of 30 degrees to a magnetic field of strength 0.4 Tesla. With velocity 3 by 10^36 meters per second. Right, and we have to calculate the magnetic force. What would I write for the magnetic force here? The formula. Well, not the formula. We know the formula. What do I substitute into this formula?
Point.
Is what, sorry? 0.4 you said? Right, 0.4 multiplied by
Will it be the charge of the proton?
right, so the charge of the proton is equal to what?
(1.6 by 10 negative 90).
Right, 1.6 by 10 to the negative 90, because the magnitude of charge of the proton is the same as that of an electron, right? And then multiplied by
Speed.
3 by 10^36 multiplied by
Sine theta.
sine theta. Right, so this is equal to what?
(9.6 by 10 negative 40).
Newtons, right? So always make sure to write your units as well. Right, so now we basically cover all the material that I wanted to cover for these practice sessions, right? The both the material and the questions what I gave, if you could know up to here, then what we do, if you're able to do this without using your textbook or using any material, ChatGPT or whatever, you will get 100% in the exam, right? So we covered even more than what was in the exam, and so if you could do up to here, you will do very well in the exam, right? So I covered all the material. Is there
I really hope, yes.
Sorry?
I really hope so, yes.
Yeah, for sure. Once you could do this, you will be able to do the exam. You will be able to get 100% in the exam.
Alright, sir. No problem.
By chance, so when you say like specific formulas, is it we have to learn those specific formulas, or or like the whole section just in case?
So you need to know all the formulas what we used for these sessions, like especially those formulas. There were other formulas that I did not cover, so you don't necessarily need to learn those formulas, but for every formula that we used in the remedial sessions, you will need to use those formulas.
Okay, done.
Right. So, are there any questions that you all have?
Yeah. So since you say you're finished, right? I know we have one last session tomorrow. Will that be for like only questions or?
Right. So, my plan was if I finish all the material in this session, well, before the final session, what we would do is we would look at last semester's paper and go through all of the answers for that paper. So that would be the plan for the rest of the session and next session if you all don't have any questions. If you all have questions, I'll make that the priority and we'll go through whatever questions you all have. So if you all don't have any questions right now, we will take a little break and then we'll start the paper from the last exam. If and then maybe by tomorrow for the last session you might find some more questions when you're looking over your notes or looking over what we did, and if you have the questions we will answer those questions. If not, we will just continue with the paper from last semester. Sorry. So if you have no questions now, we'll take a little break and we'll start back at 11:30. We'll just do like a 15 minutes of the last paper. Okay, so do you all have the paper in front of you?
Yeah.
Alright, so let's start with the first question, right? Distinguish between mechanical and non-mechanical waves, providing an example of each. So mechanical waves require a medium to propagate, whereas non-mechanical waves do not require a medium to propagate. Mechanical waves, mechanical waves, examples of mechanical waves are water waves, sound waves, waves on a string. Non-mechanical waves are electromagnetic waves, right? The second one, define the phase of a wave. And what is the relationship between a phase of pi and the wavelength of a wave? So the phase of a wave is the fraction of the wave oscillation that has been completed, right? At that particular point. So a phase of pi means that half of the wave oscillation has been completed at the position with a phase of pi. So therefore, a phase of pi is half of the wavelength of a wave. List the properties of a coherent wave. So a coherent wave waves, as we saw, they have the same wavelength, the same frequency, the same speed, and they also have a constant phase difference. So wind blows around a pipe that has one open end and one closed end. The air in the pipe resonates at the fundamental frequency of 150 Hz. Sketch the standing wave pattern produced in the pipe. So, right. One open end and one closed end. So at the closed end, there will be a node. And at the opened end, there is an antinode. This is for the fun. Well, in general, for open end and closed end, this is generally what occurs. There's a node at the closed end and an antinode at the open end. So for the fundamental frequency, we would have a standing wave pattern like this, right? There would be no other antinodes in the pipe for the fundamental frequency. Determine the wavelength of the first harmonic. So in this situation, we know that L is equal to n times lambda over 4, right? So in this case, and we could see it here, this is quarter of our wavelength, right? If we continue this, we'll have another quarter of the wavelength at this position here, where this is the other node. and then here we would have another quarter of the wavelength, and this is the other quarter, right? Sorry, I made a mistake here. That is quarter of the wavelength. Then here at this point we would have another quarter here, right, and back up to here. This is the last quarter in the center here, right? So we know that the length of the pipe is equal, so in this case L is equal to lambda over 4, right? So they asked us to determine the wavelength. We know the pipe is, so actually lambda would just be equal to 4 times L, the length of the pipe, oh, actually in this I didn't read the question properly. In this question, we didn't have the length of the pipe. They gave us the fundamental frequency, right? So we know that we have the formula V is equal to F times lambda. So lambda is equal to V over F. This would be the velocity is given at on the first page. So the velocity is 343 meters per second, and the frequency was 150 hertz, right? So this is approximately, this is 2 point something, right? 2 point something meters. Now in part 3, it asks us to calculate the length of the pipe. So we know the length of the pipe in this case is equal to lambda over 4, which is 2 point something over 4. So just do the calculation there. So I'll write it down properly.
$2.29.
2.29, right? So this will be 2.29 over 4, which is how much?
$0.5725.
0.57 meters, right? So that was part 3. In part 4, what is the frequency of the second harmonic? Now let's draw the second harmonic, right? Although the question didn't ask, just to easily visualize this, let's draw the second harmonic. So again, we would have a node here, but we will have one antinode, and then we would have a node, and then another antinode. Remember, at the open end must have an antinode, right? So at the first harmonic, basically it was this antinode was at the end of the pipe. For the second harmonic, the second antinode must be at the end of the pipe. So we have one antinode in the middle, and the second antinode is at the end of the pipe for the second harmonic in this case, right? So we could see now that the wavelength in this case is 3 times that of the fundamental of the first harmonic, right? Because we have one antinode here. Sorry, the wavelength of the fundamental harmonic in the first harmonic is 3 times this wavelength. Because we had now we fit 3 sections into the pipe. Right? So 3/4 of the wavelength now fits into the pipe, I should say, not 3 sections. This is 3/4 wavelength. If we extend this, we'll have the full wavelength if we extend it by 1/4 of our wavelength. Right? So now the wavelength in the wavelength of the second harmonic is 1/3 of the wavelength of the first harmonic. Therefore, the frequency to have the same velocity, the frequency would have to be 3 times the fundamental frequency, which would be 3 times 150 Hertz, which is 450 Hertz. Right? So that is the second harmonic. Now, for the last part, it asked, is the pitch of the first harmonic higher or lower than the second harmonic? So we know that frequency is related to pitch, in that a higher frequency means a higher pitch and a lower frequency means a lower pitch. Right? So since the second harmonic has a higher frequency than the first harmonic, the second harmonic has a higher pitch. Right? So let's move on to part C. So we had the equation y is equal to 0.03 meters sine 40 pi inverse meter per meter times x minus 20 pi per second t. Right? And they asked us to calculate what is the amplitude of this wave. So we just compare this with the wave equation. Y is equal to a sine kx plus or minus omega t. Right? So we could see that the amplitude is equal to 0.03 meters. In the second part, they asked us to calculate the wavelength. Now we could see here that the wave number, the angular wave number, is equal to 40 pi. Or this shouldn't have the inverse, right? Is equal to 40 pi. So k is equal to 40 pi is equal to 2 pi over lambda. Right? So therefore lambda is equal to 2 pi over 40 pi. So the pi's cancel, which is equal to 1 over 20, which is equal to 0.05. And the unit would be meters, right? Because k was in per meters. Then in the last part, they asked us to calculate the period of the wave. Right? So looking at this equation again, you can see that omega is equal to 20 pi. Right? So omega is equal to 20 pi is equal to 2 pi times f. Therefore f would be equal to 20 pi divided by 2 pi, which would be equal to 10 Hertz. Right? Because omega was given in per second. So the frequency is 10 Hertz. Now they asked us to calculate the period, right? The period is 1 over f. So that is 1 over 10, which is equal to 0.1 seconds. Right? You could have also done it using this formula omega is 2 pi over t, right? So therefore t would be equal to 2 pi over 20 pi, which would be equal to 0.1 seconds, right? You could also use that formula. Right, so that is question 1 of the past paper. So you see, it was not too difficult. We finished that in 15 minutes. Right, do you all have any questions? Okay, if not, we will finish for today and we will continue the rest of this paper tomorrow if you don't have any questions. But if while you're going through your stuff you find any questions, take a note of it and we'll go through those questions tomorrow.